going to look at a couple more reactions and determine if they are redox reactions or not. And if they are redox, what actually goes through oxidation versus what goes through reduction. So I take a look at my first substance, Al. Al represents a formula of an element, so I assign it an oxidation state of 0. My next substance, CuCl2, it is a compound, so that means the summation of their oxidation numbers needs to be 0. I see my anion comes from group 17. It's a halide, so I assign it a -1. But there are 2 of them, so collectively they supply a -2. There's only one cation, so the cation must be using a +2. My next formula is Cu, a lonely element, so I assign it an oxidation state of 0. My final substance is AlCl3. Cl comes from group 17. It's the second partner, so it's functioning as the halide or anion, so it uses a -1. But there are 3 of them, and there's only one of the Al, so the Al must be using a +3. So when I take a look from the left to the right, I look at Al's starting oxidation state to its ending, it's different. Cu's oxidation state starting to ending, it is different. So first thing that I'm going to note is that this is actually a redox reaction. So this is an example of a redox reaction because the oxidation states have changed. So the oxidation states have changed. So that means that there are electrons being transferred. So electrons are transferred in this reaction. Now, but if you look closely in this reaction, Cl starts off with a -1 and it ends with the same one. So in this process, I'm not going to cross the Cl's off, but I'm just going to put a line through it. So when some of your species show a change in their oxidation numbers and then ones maintain it, the ones who keep the same oxidation numbers, they're known as spectators. So they're present during the reaction, but they don't participate in the electron transfer, so we ignore them. So what remains, the non-spectators, are the ones that participate in the electron transfer, and we're going to figure out which one loses the electrons versus gaining. So if we go back up to the top, if you climb up the ladder and end with a increased oxidation value, more positive than where you started, that's Leo. So I'm going to write myself a little note right here. Leo means I see an overall increase in the oxidation number going up the ladder. Therefore, Gur means I have gone down the ladder. So I just take a look. Al goes from 0 to +3. +3 is higher up the ladder. So I know that my Leo process is dealing with the aluminums. Gur means that my oxidation state went down the ladder. Cu starts off with a +2 and it dropped down to a lower value of 0. So what was reduced is the copper. Now, if I want to get really specific of what was actually went through oxidation, that would be the Al0. This is what is actually oxidized. This is the structure that lost the electrons. The Al +3, this is the result of the lost electrons. This is formed when the structure loses the electrons. And when I take a look at the reduction process, the Cu +2 is actually what is reduced. This is the structure that actually gains the electrons. So this guy gains the electrons, and when it gains the electrons, this is what it forms or what it makes. So this is the result of gaining the electrons. Let's take a look at the next example here. So start off with assigning oxidation states. First formula, CH4. I have hydrogen bonded to a nonmetal, so it uses a +1. But there are 4 of them, so the C must be using a -4. O2, it's the only one elemental symbol in the formula, so it's an element, assign it a 0. Moving to the other side, I see this formula ends in O2. Is it a peroxide? Well, it's bonded to a group 14. Its partner does not come from group 1, group 2, nor is it hydrogen. So this is common oxygen. It uses a -2. There are 2 of them. So the first partner has to counterbalance it or cancel it out. So it uses a +4. Last example, I see that this has oxygen in it. It's not a peroxide formula. It is not bonded to fluorine, so the oxygen is using a -2. There's only one oxygen, but there are 2 H's to counterbalance it, so each H must be using a +1. My next task now is to take a look through and eliminate any possible spectators. So that would be an element that starts with an oxidation state and ends with the same one. So the hydrogens start with a +1 and they end with a +1, so they function as spectators. So I'm just going to put a line through it so that I ignore them. But carbon shows a change in oxidation state, so does the oxygen. So they are participating in the electron transfer. So Leo, losing electrons means I'm going to climb up the ladder, where Ger, gaining the electrons, means I'm gaining negative charge, so my oxidation state is going to go down the ladder. So if I take a look here, carbon starts off with a -4 and ends with a +4. So going from -4 to +4 means I'm climbing up the ladder. So my Leo is starting with a -4 and ending with a +4. Oxygen starts off with a 0 and in both cases ends with a -2. So the oxygen's oxidation states went down the ladder to a more negative value. So I go from oxygen with an oxidation state of 0, gains enough electrons to end up with a -2 charge.